Hey, welcome to another day with Klein's Calculus. We're going to look at lesson 3-4, velocity and other rates of change. Recall that velocity is simply an instantaneous rate of change, and we define that as f prime of x, that's our derivative, or our instantaneous rate of change, equal to the limit as h approaches 0 of f of a plus h minus f of a over h. So very small numbers, the difference between them, provided the limit exists. So we're going to use that idea to find rates of change in a more concrete idea, in this case in circle areas. Look at example 1. It says to you, and you're going to get some problems like this, find the rate of change over the area A of a circle with respect to its radius r. So in order to do this, when it's asking this, it's actually just asking you to find the derivative function. So the area formula we know is area equals pi r squared. So if we wrote that as a function, we'd say the area with respect to r equals pi times the radius squared. Now to take the derivative of that, pi is our constant. It's just going to come along, and the derivative of r squared, bring the 2, the exponent in front, r, and that's to the 2 minus 1, which is actually going to just be to the first power. So I can clean this up, and I can say that the change in the area, the derivative with respect to r, is just going to be 2 times pi times the radius. Kind of a neat little relationship where the change in the area is actually the same formula for the circumference. This tells me that whatever size my radius is, as it grows, this number will describe the change in the area, how much the area is growing or shrinking. Now, let's use that idea to evaluate the rate of change of A at r equals 5 and r equals 10. So we've got a radius, it's 5 units long. Well, I know that my formula is 2 times pi times the radius. So for r equals 5, I'll put in 5 here, and that's going to get me a change of 10 pi. So as my radius of 5 is increasing, the area is increasing by about 10 pi square feet, or square units. For the change in area when the radius is 10, I'm going to write my derivative again for area, 2 pi, and this time I need to put in 10 for my radius. So when I evaluate that, I end up with 20 pi, and that's the change in square units in the area. When my radius is at 10 and it's increasing, then my area would be increasing by 20 pi units for every 1 unit of radius, and it would be decreasing by 20 pi units for every 1 unit of radius at 10. Now here, keep in mind, because this change is like a slope, if r is measured in inches and a is measured in square inches, what units are appropriate for the change in area with respect to the radius? Well, I know my radius is measured in inches, so the change in radius would also be measured in inches. And I know the area is measured in square inches, so the change in the area would also be measured in square inches. And my units for the change in area with respect to the radius are square inches per inch. So if you're looking up here at this, that means when the radius is at 5 inches, that area is changing at about 10 pi square inches per inch of radius. And when the radius is at 10 inches, the area of the circle is changing by 20 pi square inches per inch. So that's how that's going to work out. And you can do this with pretty much anything using that idea of derivative. Now, we talked about the derivative being the instantaneous rate of change or the slope of a function. Well, and I talked to you a little bit last time about you can take a derivative of a derivative. Well, if you think about derivative as velocity, so you've got a position function, and then you take the derivative, and the rate of change in position would be the velocity, how fast it's going. Well then, how fast the velocity is changing would be the next derivative, and that's called acceleration. Okay, so that's how fast the velocity is changing with respect to time. And you can go ahead and you can go a few levels with this. Let's say we have s of t, and we usually denote s for our position function, equals x to the 5th minus 2x cubed plus 6. Well, my velocity function, using the power rule, bring the 5 out in front, x to the 4th minus 3 times 2 is 6, x squared, and the derivative of 6 is just 0. So there's the velocity of this object with respect to time. And since I've got t's there, I should have t here. It doesn't matter which variable you use, but it's pretty important to use the same one. Now if I want to take the derivative of the velocity, the change in the velocity, that's going to give me acceleration. So 4 times 5 is 20, t to the 4 minus 1 is 3, minus 2 times 6 is 12, t to the 2 minus 1 is just t. Now there's one more level you can go, and I think we're going to hear about it next chapter, but I'll just tell you now. How fast does acceleration change? Think about when you accelerate really fast, and you might push down on that accelerator and your car gives a little jerk before it actually shoots forward. That's the derivative of acceleration. It's called jerk. And so if you took the 4th derivative down, you'd say 3 times 20 is 60, t squared, minus, this would be t to the 1st power, so 1 times 12, and t to the 1 minus 1 is t to the 0 power, so that just went away. So that would be your derivative, this would be your first derivative, s prime of t. This would be your second derivative, s double prime of t. And this would be your third derivative, s triple prime of t. And you can even go you could even go s to the 4th, and I think on your homework you might be asked to find the 4th derivative, and if you did, you'd have s to the 4th, s to the 4 prime of t. And if you did that, what would we get? 2 times 60 is 120 t, 2 minus 1 is 1, and this would be a 0. So you can take as many derivatives as you like, just keep on going down, and you can tell they get increasingly simple. And we're going to look at, speaking of acceleration and position and velocity, we're going to be looking at some of those types of problems. So some fun facts to know, put in your notebook and keep track of. Free fall constants on Earth with gravitational pull using English units. The coefficient for gravity is 32 feet per square second. So if you're looking at a function, it would be half of that. So s equals 16t squared, you know that we're talking about feet, if you've got the 16 there. Because in metric units, the gravitational pull is 9.8 meters per second squared, then in our metric system we have 4.9 t squared with s in meters. So just good things to know in general. And we will look now at that idea of modeling vertical motion, something falling or being launched. In this case, we're going to have a rock falling, sort of. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, about 109 miles per hour. It reaches a height of s equals, and that s is telling you we're looking at the position, 160t minus 16t squared feet after t seconds. So you know its path. If you're thinking over time, you'll have a graph that'll look like this. It'll go up and it'll come down, and it's going straight up and straight down, but this is time. So time is going to march on, and the rocket will be at some height at every time. So how high does the rocket go? Well, I know in pre-calc you guys just simply graphed it and found your maximum. In calculus, we're looking to do things a little differently. we know that those max and min values occur when the velocity equals 0, because it's coming up, hesitates for just that second, and then it comes back down. The velocity for just that second, when it's at a maximum, will be 0. So what we will do is we're going to look at this function, and we'll just take the derivative, set it equal to 0, and find that velocity. So I know v of t is going to be, the derivative of this is just 160 minus 32t. Now, all I need to do is I'll set that equal to 0, add 32t to both sides, and then divide by 32. So t equals 160 divided by 32, and I think that's going to be 5. 5 times 2 is 10, carry the 1, there we go. T equals 5 seconds. So I know that the maximum value was reached at 5 seconds. That's when it's at its max height. But now, I need to put it into the position function to find out what that height is. What's the height at t equals 5? So I'll put s of 5 equals 160t times 5, minus 16 times 5 squared. And I'll say 5 times 0, 5 times 6 is 30, 5, 6, 7, 8. And I've got 16 times 25 here. Well, 4 times 25 is 100, so this must be 400. So it's going to reach a height of 400 feet. Notice we can do that without a calculator and without too much trouble. Now, what is the velocity and speed of the rock when it's 256 feet above the ground? Notice it's going to have that height twice, on the way up and on the way down. So to do that, you're going to take your velocity function, v of t, equals, your position function, s of t. We want to know when it's 256 feet above the ground, equals 160t minus 16t squared, and we're going to have to put 256 feet right in here. And I use position function because I want to know the height. Well, I can't solve this sort of thing, but if I take away 256 from both sides, then I'm going to, I'm going to take everything else away here and get more positive. So I'm going to have 16t squared minus 160t plus 256 equals 0. Now, I'll factor out my 16, or you can just count max on this. And you want to find, if I factored out my 16 here, I've got t squared minus 10t plus, and 256, that's going to give me 16 times 16. And then I can factor that, t plus and t, I need two minuses here. What two factors of 16 have a sum of 10 must be 8 and 2. So I know the time when times are going to be t equals 8 seconds and t equals 2 seconds. T equals 8 seconds, t equals 2 seconds. That's the times when this is 256 feet above the ground. So now what I'm going to do is find the velocity at those times. So I'm going to have velocity at time 2 is 160 minus 32 times 2. So 160 minus 64, 96. And I've got feet per second. And the velocity at time 8 is going to be 160 minus 32 times 8. Well, that's 160 minus, I'm going to have to do that one. 8 times 2 is 16. Carry the 1, 8 times 3, 24, 25. 256, so that's going to be a negative velocity, 160, 96 feet per second, I believe. So negative 96 feet per second. So that negative just says it's going down. Okay? And I'm going to run out of time on this video, so we will talk about the rest of this in the second part.